Well, hello everybody. Thank you to Olivier and Leon for the invitation to join this school. It's a great shame we're not meeting together in Saarbrücken, but it's good to see everybody over the web. So in this lecture, I'm going to be talking about the origins of magnetism. And this is where I'm talking to you from. This is Oxford, where I am in the United Kingdom. Here you can see the River Thames that goes through the side of Oxford, and here's a close-up of the centre of the city. So it's an old medieval city, and as you can see, characteristic British weather, blue skies, sunny every day. And so if you want to think more about some of the topics in this lecture, here are some of the books. I think Olivier in his lecture recommended a number of these books already. I suppose I should mention the ones that I've been involved with. So there is my magnetism book. There's a very short magnetism, very short introduction if you want to read about some of the historical parts. And if you want to delve further into the theory, there's the book on the right, Quantum Field Theory for the Gifted Amateur, that Tom Lancaster and I wrote. Okay, that's it for the commercials. So on to the lecture. And what I plan to do is in the first 40 minutes of the lecture, I will aim to treat the first 4 items in this list, and then in the second half of the lecture, after a brief break, I'll talk about the final 3. So what I'm going to do is explain a little bit about why classical mechanics is not good enough. That's the Bohr-van Leeuwen theorem. I'll talk a bit about orbital and spin magnetism, which are the basic sources of magnetism in many magnetic materials. I'll say something about spin precession because that's something that's very unique to magnetic materials. And then I'm going to talk about the origin of the magnetic moment in a number of different magnetic atoms. That's Hund's rules. And then I will review diamagnetism and paramagnetism and finish up by saying some things about orbitals and the crystal field. And that will explain where this strange phenomenon of orbital quenching comes from. And as you'll see in this, there are a number of themes that run all the way through. So let's begin with the Bohr-van Leeuwen theorem. Now what I'm going to do is go right back to the beginning of how we might treat magnetism in a material and think a little bit about the Lagrangian. So good French mathematician and physicist Lagrange noticed, as did a number of other people working at the same time in France actually, that there was another way of formulating classical mechanics in addition to what Newton had done a century before. Newton, as you all remember, talks about force and the change of a momentum, but Lagrange's view was that you could actually recreate classical mechanics by formulating a Lagrangian. And Lagrangian is basically the difference between the kinetic energy and the potential energy. So what we could do is we could think about the Lagrangian for a charged particle in a magnetic field. Now here it's helpful to use a bit of insight from Albert Einstein. And as you will also remember, magnetism is a relativistic phenomenon. It involves always moving charges. The observer is, the charges are moving with respect to an observer, and that creates a relativistic correction, which is the magnetic field. So when you go into special relativity, what you may remember is that everything is described by 4 vectors. There's a scalar part and a vector part. So for example, you have the velocity 4 vector, which is the speed of light, and the ordinary 3 velocity. And similarly, the magnetic vector potential has 2 parts to it. The first part is the scalar potential, the usual electric potential, and then there's a vector part, a 3 vector part. And if, as you may remember in relativity, if you make your indices go downstairs, you have a minus sign. So the Lagrangian for a charged particle in a magnetic field is kinetic energy a half mv squared, the usual kinetic energy. And then what you subtract is q v mu a mu. And when you expand out that scalar product because of the minus sign, you end up with that form that's written in the blue equation, a half mv squared minus qv plus qv dot a. Now, if you then want to get back and define something called the momentum, what you do is you differentiate your Lagrangian with respect to the velocity, the rate of change of the coordinate part of your representation. And when you do that, you get mv plus qa. And that's a very important equation, because when you then go back to writing down the Hamiltonian, and now we introduce the Irish physicist William Rowan Hamilton, if you form his Hamiltonian, you then end up with something that looks like half mv squared plus qv. So where is the magnetic vector potential gone? If we write a half mv squared in terms of the momentum, we end up with this term p minus qa all squared over 2m. And if you go through the prescription of Lagrangian and Hamiltonian mechanics, you can go back to
sorry to interrupt, Steve. Do you have some means to use a pointer, or so that we check where you are?
Okay, I'll do it. Thank you. Okay, so if we end up at this final equation, the green equation, then you have that the force is equal to the familiar Lorentz form. So I haven't filled in the steps for that. That's something that those of you that know about Lagrangians and Hamiltonians can prove to yourself. But you recover the famous Lorentz force law. So this all holds together. Now, that's a lot of mathematics. So what's the key thing that I would like you to take away from this? Well, that's shown in the next slide, which is basically the effect of a magnetic field on a system of charged particles is to turn the momentum, P equals mv, to P equals mv plus qa. So the momentum has an additional part added to it. And so therefore, as I said on the last slide, the kinetic energy, a half mv squared, becomes this new form, P minus qa all squared over 2m. Now there's a very important point I want to just get across about this. When you introduce a potential, there is always this thing called a choice of gauge. Now you're familiar with it in electric potential, because if you say that you are currently at 100 volts, that doesn't mean anything. We don't really have any sense of potential. What's important is potential difference. If you're at 100 volts with respect to the ground, then you shouldn't touch the ground, otherwise you will be electrocuted. So it's potential difference that's important. So the absolute zero of potential is whatever you like. And that shows that the electric potential has a freedom of choice associated with it. But the magnetic vector potential has a bigger freedom of choice, because you can always add on the gradient of a scalar field. And when you take the curl of it, you end up with the same magnetic field, B. And it turns out, and I'm not going to go into the details of this, that the choice you make for electric potential and magnetic vector potential also affect your choice for the canonical momentum. So the thing that you have to be sure of that's real is mv, because velocities are real quantities. They can't depend on your convention. So a half mv squared is a gauge invariant formulation. But P minus QA all squared is also gauge invariant, because the choice that you make with A then affects the choice that you make with P. Now this will be important later. But for now, what I just want you to remember is the fact that the only effect of a magnetic field on a Lagrange is this change, the shift of taking mv, adding qa to it, and giving you the momentum. Now bear in mind that this is all classical, so there's nothing quantum yet. Now the theorem I want to tell you about comes from these two people, Niels Bohr and Hendrika van Leeuwen. Niels Bohr did this in his diploma thesis, which he wrote in Danish, and so I'm afraid nobody read it because not enough people speak Danish. So Hendrika Johanna van Leeuwen, she reinvented it later, but she published, and she published in I think a Journal de Physique. So therefore people read it, and she did work completely independently, so it's known as the Bohr-van Leeuwen theorem. And actually her paper is a lot clearer than Niels Bohr's. So what did they do? Well, the theorem is quite technical, but really I've given you the key idea here. Now, essentially, what they were trying to do was calculate how charged particles whizzing around in a box, interacting by purely classical effects, how they would behave when you apply a magnetic field. And the way you do this in thermodynamics is you write down the partition function. And the partition function is essentially just the sum of Boltzmann factors. Boltzmann factors are e to the minus beta. Beta is 1 over kt times the energy. And the energy depends on the position and the momentum of all of the particles. And so what you do is you integrate over all of the positions and all of the momenta. Well, essentially what Niels Bohr and Hendrika van Leeuwen realized was that if you do this problem and you repeat it in a magnetic field, all you do is you change the momentum, P, by a constant amount. So you shift all of the momenta by a constant vector. So what that essentially means is when you work out the partition function, doing these integrals, but you're shifting the integrals by QA, at least the momentum integrals. But because we're doing this classically, and so the momentum can go anywhere between minus infinity and plus infinity, this is just a change of variable. It doesn't affect the integral. So Z is unchanged, the partition function. And if the partition function is unchanged, so is the free energy. And if the free energy is unchanged and doesn't depend on magnetic field, then the magnetization will be zero. So essentially what they proved is assume classical mechanics and the magnetization is zero. In other words, all magnetic materials have zero magnetic moment. In other words, if you've ever seen anything that's magnetic, you must have imagined it, because there is no magnetism. So something must be wrong. And of course, what's wrong is the assumption that classical mechanics holds. And in fact, they had another proof of what's going on, because if you take a group of charged particles in a box, and here I've drawn my box to be arbitrary shape, then of course you might imagine that if you apply a magnetic field perpendicular to the screen, all of the electrons would go round in circles, or all the charged particles would go round in circles. Surely that would produce a magnetic moment. But what they also realized is any charged particle that is near the boundary will reflect off the boundary and go around and do an orbit in the other way around this volume. And what they were able to show is that if you add up all of the magnetic moments in the center, they are cancelled out precisely by all of the charged particles moving around the edge. So you can do it in a number of different ways, but basically what they've proved is that if you assume classical mechanics, there's no magnetization. So the Bohr-van Leeuwen theorem is very important because it tells us we have to use quantum mechanics. Okay, so therefore in the rest of this lecture, I'm going to use quantum mechanics. So we move on to our second topic, and our second topic is orbital magnetism. Now, the basic idea with orbital magnetism is that if you have a charged particle going around an atom, that is associated with a current. So if you have a charge Q going around a circular orbit, and sorry, I tried to draw a circle, with velocity v around a circular orbit of radius r, then we can do a very quick calculation. We can work out the current, as I've done here. And if we've got the current, we can also work out the magnetic moment. The magnetic moment is the current divided by the area. And so the, hold on, that's not right. That should be multiplied. I'm so sorry, I've got that the wrong way around. That should be the current times pi r squared. My apologies, I'll have to correct that in the notes. And when you then work out the magnetic moment, you then get the gyromagnetic ratio, Q over 2m, times the angular momentum, which is mvr. So apart from my dodgy middle step, the important thing about this equation is that it shows that there is a linear relationship between the magnetic moment, mu, and the angular momentum, L. And that's very important because it's going to be very important for us later, but also it makes a lot of logical sense, because if you have a charge going around an orbit, you also have mass going around an orbit. And if mass goes around, you have angular momentum. And if charge goes around an orbit, you have a magnetic moment. So magnetic moments, and as we know that's going to be important for magnetism, is connected with angular momentum. So that's going to be very key to us. And the thing that connects magnetic moment and angular momentum is this quantity called the gyromagnetic ratio, which is just the charge divided by twice the mass. Now here we have a slight problem been bequeathed to us by the early workers in electromagnetism, who chose the charge on an electron to be negative. It was completely arbitrary which way they just defined positive and negative. But because we're usually dealing with electrons which have negative charge, what that means is that the angular momentum is usually in the opposite direction to the angular momentum. That's because mass goes around one way, but charge, as we defined it, goes around the other way because electrons are negative. So that's something to remember for later on. Okay, now let's do some quantum mechanics. Let me first of all, in this top equation, remind you of something that you hopefully remember from your undergrad quantum mechanics. So the momentum operator in the x direction is given by minus IH bar d by dx. And when you have an operator, what you can do is you could work out its eigenfunctions. In this case, it's fairly obvious what the eigenfunction is. It's e to the I kx, it's a plane wave. And if you operate on that eigenfunction with px, you will get h bar k times e to the I kx. So the eigenvalue is h bar k. So what this tells you is that if you have a wave with wave vector k, it has a momentum of h bar k. Well, when you go to angular momentum, you end up with a very similar equation. The angular momentum operator in the z direction is minus IH bar d by d phi. Phi is the azimuthal angle. So by analogy, our eigenfunction is e to the I, let's call it m phi, and the eigenvalue is mh bar. Now here m is a quantum number. I don't mean mass, it's a particular quantum number, and we have a different feature than we had for linear momentum. In linear momentum, k could take anything. K is just 2 pi over the wavelength. But when we're dealing with angular momentum, we have a difference, and that's because phi has to be defined on a circle. So that means when I do e to the im phi plus 2 pi, I must get back to where I started with. I must have single valued functions. And so the consequence of that is m has to turn out to be an integer. And so it is indeed an integer quantum number. So the other thing we found is the z component of the angular momentum is going to have to be a quantized quantity. Now, again, I'm telling you things that you will have encountered in an undergraduate quantum mechanics course, but the angular momentum operator is just r cross p. And so if we do this in 3 dimensions, it takes a more complicated formulation. The LZ operator I can write in Cartesians as well as in spherical polars. And you will remember that if you take the angular momentum states, they're characterized by 2 quantum numbers in such a way that the LZ operator gives you this eigenvalue mh bar, as we've already seen, and the L squared operator gives you an eigenvalue L into L plus 1 h bar squared. Again, this is something familiar from an undergraduate quantum mechanics course. But if you work out what these eigenfunctions actually look like in terms of coordinates, they turn out to be spherical harmonics. And I'm going to come back to this at the end of the lecture. These spherical harmonics take the form of an associated Legendre polynomial, which is some complicated function of cos theta, and the phi dependence is, just as I anticipated, e to the im phi. So the second part of this slide is more complicated, but the first part is hopefully fairly easy and very important for what comes up later to remember this e to the im phi part of the wave function. Okay, well, that's all I'm going to say about orbital magnetism for the time being, but I will return to it in the second half of the lecture when I talk about orbitals and the crystal field. Okay, let's now move to spin magnetism. So even though I'm presenting a lot of theory, we should remember that our subject is based on experiment. And one of the key experiments done in the 1920s was the Stern-Gerlach experiment. And what happened in the Stern-Gerlach experiment was a beam of silver atoms. It would have been nice to use electrons, but unfortunately electrons are charged. The great thing about silver atoms is they have an extra unpaired electron associated with them, but the overall atom is uncharged, so you can pass it through a magnetic field without worrying about any additional bending effects because there's no charge. So the silver atoms were passed through this inhomogeneous magnetic field. So my little sketch of a north and south pole, but one of them being pointed, one of them being flat, this gives you an inhomogeneous magnetic field. And as we heard from Olivier's lecture earlier on today, if you have an inhomogeneous magnetic field, then you end up with a force on a magnetic dipole. If the field is uniform, there is no force. And what was discovered, rather interestingly, was that there were two outcomes to this experiment. Either the silver atom moved upwards, in other words, there was a vertical force upwards, or there was a vertical force downwards, and the silver atom moved downwards. So that seems to suggest that there were two different spin states, as we now call them, for the silver atoms. And we believe the same works with electrons. So if we wanted to describe this system in quantum mechanics, what we need is a Hermitian operator for a two-state system, and that will always be a 2 by 2 matrix. So I'm just going to do a little bit of mathematics here. Those of you that don't like the mathematics can tune out for a moment, but I think this is maybe quite useful to derive the famous Pauli spin matrices. So what we need to do is look for a Hermitian operator. Remember, Hermitian operators have real eigenvalues, and we should look for one which is a 2 by 2 matrix. So the general form Hermitian operator for a 2 by 2 matrix looks like this. It has real parts along the diagonal, and the off-diagonal parts can be complex, but they're complex conjugates of each other. So one of them is C plus ID, and the other one must be C minus ID. Now we want this Hermitian operator to have eigenvalues plus or minus 1, corresponding to the two beams either being upwards or being pushed downwards. Of course, it could be plus or minus a constant, and of course that constant will be h bar over 2, but I'm not going to worry about that at the moment. We're just going to say there's a positive answer and a negative answer, which we will encode with plus or minus 1. Now, to try and find out what kind of matrix would obey this, we can use the fact that the trace of the matrix is the sum of the values, and therefore is 0, and the determinant of the matrix is the product of the eigenvalues. Well, a little bit of algebra tells you then that B equals minus A. So in fact, the diagonal elements along these matrices, in these matrices must be, one must be negative of the other. And the other condition we then have is that A squared plus C squared plus D squared is 1. This comes from the determinant. So we now know a lot more about these matrices. Okay, well, let's make a guess. The simplest matrix that satisfies this, that has the diagonal elements to be negative of each other, and A squared plus C squared plus D squared is 1, gives you this very simple matrix which has 1 and minus 1 along the diagonals. Obviously that has eigenvalues plus 1 and minus 1, and the eigenvectors, you can just kind of read them off. They're 1, 0 and 0, 1. So we're going to call this our Pauli spin matrix along the z direction. Just by convention, we'll choose the z direction to be special. Now we've got two states. What we can do is we can write a general state as being the sum of the up state and the down state with some complex numbers before them. And we call this state a spinor. So we'll write it as a little vector alpha beta. And of course, if you want to work out, for example, the expected value of the sigma z operator for this state alpha beta, you can just work something out like this. So here is the ket psi, that's our spinor. Here is the bra version, that's where we've taken the ket and we've turned it into a row vector from a column vector, and we've taken the complex conjugate. And now if you work that out, you then just get this expression. So we can do calculations like this. Okay, so that's our first spin matrix, and experiment tells us that the angular momentum is h bar over 2. So I will put that in the front for my spin z operator. Okay, now what I want to do is to see if I can find the other Pauli spin matrices. Now the other Pauli spin matrices must basically give me 0 when I work out the expected value of the states up z and down z. And that's because they are perpendicular to z, so therefore there should be no component along x or y. And so if I pick a perpendicular component, in fact anything perpendicular to z, I should get 0. So a general perpendicular, the sigma x or sigma y Pauli spin matrix would give me 0. And if you work this through, that tells you that the diagonal element A is 0. So that means my general perpendicular Pauli spin matrix must take this form. 0 along the diagonals and C plus ID or C minus ID on the off diagonals, with C squared plus D squared is 1. So one way I can write this, C plus ID I can write it as e to the I phi. Just write it as a phase factor. That would satisfy this. So my general form of these perpendicular Pauli spin matrices looks like this. So again, I'll make a simple choice. Let's choose phi equals 0. And when I choose phi equals 0, I get this matrix, sigma x, and this is the Pauli spin matrix in the x direction, and I can work out its eigenvectors. So now I've got two Pauli spin matrices. I've got the x1 and z1. And to work out the y1, all I need to do is just go through this whole thing again and find a matrix sigma y of this form that is perpendicular to the x state. And when I work that through, I end up with an equation that gives me phi equals pi over 2. And so now I end up with the sigma y matrix. And there you can see its eigenvectors. So we now have our Pauli spin matrix, h bar over 2. Multiplying it gives us the spin operators, which you can see now at the bottom of the screen. So you may have seen some of this before, but I think it's rather a nice thing to actually derive it. Okay, so now we've got our spin operators. We can do various other things. We can work out the raising and lowering operators for those of you that are interested in that kind of thing. And we can write down general spin states going above spin a half, which then take the forms at the bottom of that slide. But I'm not going to use those particularly. I just include them there for completeness. Okay, we've got our spin operators. Something that's going to be very important when we come on and look at exchange tomorrow is if we take the dot product of two spin operators, then we end up with this kind of expression, Sx, Sx, Sy, Sy, Sz, Sz, for the two spins A and B. And these raising and lowering operators are rather useful because what they can allow us to do, if we define them as written here, is they allow us to re-express the x and the y part of this expression in this form. And why these raising and lowering operators are so important is what they do is a raising operator, for example this one, will take a down spin B and turn it into an up spin. And this is coupled, as you can see, with S lowering for A, which takes an up spin on the A site and flips it and makes it go down. So what that operator there does is it takes you from this arrangement to the one on the right. And similarly, the first part here takes you in the opposite direction. So something that's very important to remember is when you see something like SA.SB, this is something that is causing flip-flops. It has a part that doesn't cause any flip-flops, but it has a part here that causes the spins to flip. And that is going to be important in some of the later things that we look at and in some of the other lectures. Okay, so of course, those sorts of operators are going to be very important when we start looking at antiferromagnets and ferromagnets, but I'm not really going to talk about the exchange operator until tomorrow morning. Okay, good, I'm doing fine for time, so we have a little bit more work to do before taking a short break, and we're now going to look at spin precession. So here's what happens with spin precession. You have a magnetic field, let's say we have it along the z-axis, and we have a magnetic moment coming from an electron or a proton or an iron atom or a muon. I happen to work on muon spin rotation, so I often think of this as a muon precessing, but it can be whatever you like. And let's say the muon or the magnetic moment is initially at an angle theta to the z-axis. So what will happen is, even though it would save energy if the magnetic moment aligned with the magnetic field, what actually happens in a magnetic field is that the spin will precess. And I just want to point out that this is very different from electric dipole moments. Now, if you were paying attention in Olivier's lecture this morning, you probably would have thought that some of the calculations he was doing, looking at stray fields and dipole moments and a lot of those sorts of things, actually you could do exactly the same thing with electric dipole moments. In some ways, that's often more familiar, because we often study electric fields before we go through and study magnetic fields, and electric dipoles before we study magnetic dipoles. So you might be forgiven for thinking that magnetic dipoles are exactly the same as electric dipoles. All we're doing is just transferring language from one case to another. But spin precession is a rather different feature, because electric fields do not do this. If you put an electric field along the z-axis and you have an electric dipole moment at an angle theta, it will not precess. And if we were doing this in Saarbrück and it was possible to be more interactive, I would ask the audience why this is. I don't think it's practical to do this, but I'll just give you 10 seconds to think about it. Okay, and the answer is that, as I said at the beginning of the lecture, magnetic moment is connected with angular momentum, because what you have is some kind of charge going around, at least for orbital magnetic moments. Electric dipoles, you don't have any angular momentum, it's just a positive and negative charge separated. So because a magnetic moment has angular momentum, that's why spin precession occurs. Now, we can derive this in a number of different ways. Let me first of all do it classically. So as we heard in the first lecture, the energy of a magnetic dipole moment in a magnetic field is just minus the dipole moment dot the magnetic field. But there is also a torque. So if you have a magnetic moment in a magnetic field, you have a torque, which is mu cross B. So if you put those equations together, and you think about the rate of change of angular momentum, you can then show that the rate of change of angular momentum, which is of course the torque, is then equal to mu cross B. And we need this factor gamma here to relate angular momentum to magnetic moment. And then what we can do is use the geometry that I sketched in the previous slide, and then we can just solve a little differential equation, which I've done for you there. You can fill in the details later if you want to, and you just predict spin precession. So the z component of the magnetic moment stays fixed, but the x and the y components vary according to cos omega t and sin omega t. In other words, they go round in a circle. So we have spin precession, and the rate of spin precession is just gamma times b. I'm very sorry I put a subscript mu here, but that's because I'm usually thinking about muons when I think about precession. So I'm sorry about that. It should just be gamma b, I think, using the notation that we've been using in the lecture so far. Now, I did that classically, but of course, as I said at the beginning, we really ought to be doing things quantum mechanically. And by accident, it turns out that for this particular problem, for rather deep reasons, the classical solution and the quantum mechanical solution give you the same answer. So let's just do this quantum mechanically. So quantum mechanically, as I said, a general state of the system can be written as a spinor, just as a sum of states of up and down. My Hamiltonian here is minus mu dot b, so I can use all of the equations I've got so far. The magnetic moment is just gamma times the angular momentum. I'm just assuming spin angular momentum here. So I've now got this Hamiltonian, which just depends on the Pauli spin matrix in the z direction, so it looks like this. So what you basically find are two energy levels, one that goes, I'm very sorry, one that goes up and one that goes down. Sorry. This is the problem. When I move the mouse, it advances the slides, which is why I was a bit reluctant to use the mouse. Okay, so those are the energy eigenstates. But when I implant, also when I start off with a magnetic moment along a particular direction and along the direction I was showing in this initial slide, What I have started with is a superposition. So let me just try and solve this. I can do this in a number of different ways. So this slide just shows you how you would derive a Pauli spin matrix in a general direction. So for example, we could take a general direction, nx, ny, nz, and construct the Pauli spin matrix for it, and we would end up with this matrix that you can see here on the right. And this has these particular eigenstates. And so in fact what we would be doing is we would be starting off with our spin, let's say in this eigenstate. So those are my Pauli spin matrices. Just to remind you, those are the general states. And so what I can now do is start off with my, and again you can see I've got muon polarization here because I'm always thinking about muon precession. But you start off with your spin initially in this state, and then we have our time dependence given by the Schrödinger equation. That means we can take these as energy eigenstates, put on the appropriate phase factors that comes from the Schrödinger equation, work out the expected values using the methods I've shown on the previous slide, and we end up with exactly the same answers as we got for the classical approach. Now, if you really want to, you can do that by another method. You can use a time evolution operator, and then you can take the time evolution operator, and there's just a little bit of algebra here. You take the time evolution operator, you hit it on the state of the system at time 0, and when you work that out, you end up with your state of the system at a later time, and in fact you then follow the previous calculation. And I've omitted this from this talk, but those of you that know about density matrices, you can also do exactly the same calculation with density matrices, and you get the same answer. Okay, so that's a rather long and complicated way of showing you that the classical result and the quantum result give you the same answer. But maybe just before I pause, let me just say something about physically what's going on in the quantum case. So in the quantum case, we have, if we apply a magnetic field, we have these two eigenstates. And an eigenstate, if you remember from quantum mechanics, is a stationary state. So if you started off with your spin along the magnetic field, so in other words, if you were purely in, let's say, this lower state, or purely in this higher state, that state would stay there forever. But because you have your magnetic moment as an angle that isn't 0 or pi to the applied magnetic field, you are then in a superposition. And a superposition ends up giving you interference between the two different energy eigenstates. So something that is very important to remember in quantum mechanics, if you have your system in an energy eigenstate, it will do nothing. The world will be very boring if systems just exist in energy eigenstates, because nothing happens. They're stationary states, and they stay in those states for the history of the universe. So the only reason the universe is exciting is because we have superpositions. Once you have a superposition, you then have interference. And when you have interference, you have time dependence. So in the case of this particular two-state system, that interference gives you spin precession. Now, why is spin precession important? Well, it forms the basis of a number of different experimental techniques. So one very famous one is NMR, nuclear magnetic resonance. Another famous one is ESR, or electron spin resonance. And both of these techniques are used heavily in magnetism research. There is also the experimental technique I work on, which is called muon spin rotation, which also works with this process of spin precession. And of course, in work on ferromagnets, the technique is ferromagnetic resonance, FMR, where the thing that is precessing is not an individual spin, but is the whole magnetization of the system, all the magnetic moments going around. And so that's a very, very important experimental technique. Okay, so I've done the first 4 parts of this lecture. I've talked about the Bohr-van Leeuwen theorem, why classical mechanics is not enough. I've introduced the two types of magnetism that we have in materials, orbital magnetism and spin magnetism, although I haven't yet told you how to combine them. And we've said a little bit about spin precession, what happens to magnetic moments when we put them in magnetic fields. But I see it's now 25 past, so maybe this is a good moment to have our, I think it's a 5-minute break, isn't it? So I'll pause there.